Yeah. So today we have with us Professor Dennis Bondar, who's joining us from Tulane. He did his PhD at Waterloo and was then at Princeton. And today he's going to tell us about quantum system identification. And yeah, the floor is yours.
Thank you, Anwash, for opportunity to present this work. This work is actually very recent. It's just based on the preprint, which means that things might change as this project evolves a bit, but I think overall picture is here. And it's actually great to present this work, even though it's not 100% complete, because I hope we'll have a nice conversation and get some feedback and things like this. So as you can see, this work is a collaboration between us at Tulane University, which is based in New Orleans, Army Research Lab, Kurt Jacobs, who works there, famous researcher in quantum technologies, and our friends and collaborators from Czech Technical University in Prague. My name, as well as my graduate student name, who is on this project, actually, as you can see, I color them I color our names in the Ukrainian flag because we are actually originally from Ukraine. And I left in 2005 to Waterloo to study PhD. Zahar has joined me only 3 years ago actually. Yes, so of course these events unfortunately are too close, and in fact the student actually he went back to Kyiv just before the invasion to actually renew his visa, which was a worst time to renew his visa, obviously. And it's a terrible story to say, but I was pleased to see that at your institute there was a statement expressing solidarity to Ukraine. That was very nice statement. Actually, I appreciate this. We appreciate, all of us appreciate a lot of this. And of course, unfortunately, the German federal government is very supportive as well on words, but on the action, it's a little bit things are behind. And hopefully this will change. Hopefully this will change. This is quite a serious war. It's not just kind of another local conflict. Its repercussions, as you were all aware of, will last long. And I would like to, on my end, I would like to add that as a member of science community, I'm trying to also, there's a lot of discussion about Lend-Lease, right, the program to support the Ukrainian military, but also Ukrainian scientists and educational institutions. They also need support, and many universities across Europe, and in particular in Germany, have actually extended the support very generously, and it's again very much appreciated. So I call this like a brain lease. I like to call this as a brain lease, and this is as important as actually as having an economic immunity at this point. And so thank you for this to people of Germany. This will be remembered. Let's put it this way. So as the end of the politics, I wanted to just quickly mention the title, right? So we are talking about identification of quantum systems, and this is a very important problem because nowadays, so what do we mean identification of open quantum systems? The problem is, it's actually very easy to state, but it's hard to actually solve, is that you're given some hardware, for example, here's an IBM quantum computer, which you say it's quantum, right? It's working, it's functioning well, it can it gives some reproducible measurements. And you would like to say how quantum is it, how quantum, and what kind of, by which model can it be described? And so the idea is that the identification means converting measurements into actual mathematical models, into equation of motions that it can describe, that characterize this device. Now, it's important to say that it's a trivial thing, but it's very important that all devices are open, all quantum devices are open, especially in the current age of near-term quantum computing. They're noisy, they're open, and this open effects is a very, very important thing that needs to be taken into account when formulating a model for such a system. Now, luckily, we are not the first. It means the quantum research community is not the first to ask this question about converting measurements into mathematical models. This is a long problem that has a very distinguished history in engineering, actually. And it's called system identification. So the name system identification comes from engineering. And here's I give you just a textbook here, one of textbooks. I just like that textbook. That's the one that I kind of introduced me to the area of engineering systematification. Right, in engineering, you have a very complicated system, right? Like a shuttles, like a Hubble telescope, which depicted on this cover of this page. And they're a really complicated system, and very often you want to have a simple model, as simple as possible model that would be able to characterize, to accurately model the behavior of a realistic system, so that you can achieve the control of your system. So this is exactly the same problem that you would like to have with quantum devices, right? We would like to have models which are realistic, which describe realistic systems, so that we can implement controls, right? To implement quantum operations. So if you open a textbook or quantum information science textbook, by now there are many of those, pretty much every textbook will have a section on tomography. And quantum process tomography is one of the kind of, we can say, the first way, one of the basic way of converting tomographic measurement of states into information about the device, the channel, the quantum channel, as they call it. More often, there is this kind of a sub-distinct area, sub-area of open quantum system identification is Hamiltonian identification, where you actually, where you care about the identifying, where you kind of assume that the openness is not as important, and you would like to identify the parameters of the Hamiltonian. However, this is a little bit misleading, because once you have an open system dynamics, the separation between dissipator and unitary part, like dissipation evolution and unity evolution, is not that unique, and therefore it's much more well-posed problem to do the full open quantum system identification, in my opinion, rather than focusing on just Hamiltonian identification. So the ideas from engineering, like the ones, for example, described in these methods, have inspired already some algorithms for quantum technologies. So the first two references actually, in fact, here's actually kind of it's two papers, both published by Jean and Sarovar, both for Hamiltonian identification and open system identification, and more recently our collaborator Kurt Jacobs also led a project on using the tools of these tools of engineering that enable to derive novel master equations in quantum physics. Truly, like, not just a model of not just some acute computational model, but actually new insights, new physical insights were able to be arrived at employing the tool of system identification. And of course, the formulation of open quantum system models from data is actually still ongoing. And here's a couple of more recent references. And actually, the list is kind of, this is not a representative list. There are many more papers, but these are the ones that actually focus on open system identification. There are many more literature focusing on Hamiltonian aesthetic parameters. So outline of my talk is basically made of three sections in the kind of increasing level of complexity. We'll begin by showing kind of an example which will set the tone for the rest of it. Very quick example of identifying unitary evolution. It's not a very realistic example, as I will say. Then we will talk about two more realistic examples of identification of the Kraus map. And also we'll talk about how you can define Lindblad master equations from Lindblad equations. And then we will draw some conclusions. So let us begin by looking at this simple example, which will, as I said, set the tone, gives the kind of idea behind all of these methods. Let us take a very unrealistic scenario where your quantum device is basically unitary, and its evolution is described by a pure wave function, right? Pure state, or given by wave function. And let's say you are given a sequence, a time series of the wave functions, and in such a way that, for example, that it takes there's an unknown unitary operator that takes you from the initial state to the first state, And then the same unitary operator that takes you from the first state to the second state, and so on and so on until you reach the final state. Right. So each of this state is like this unitary transformation, the same unitary transformation that kind of switches between this time series. And so the question is that how, given the sequence time series of wave functions, how can we identify a unitary evolution? Now, this problem has many solutions. As I said, it's not realistic because it doesn't take into account any openness, and even does not even take into account the fact that your state is actually more, in practice, it's never wave function. It's always dead, some kind of dead state, which is always right, rather than the wave function. But so the point of this example is rather methodological than practical. So as I said, the unitary evolution connects two neighboring time points, right, as shown here. By taking left-hand side minus the right-hand side and taking a norm of this operation, and sorry, this norm of this vector norm of this difference, and summing up, right, we can ask ourselves this minimization problem that we would like to find a unitary U such that it minimizes errors, right? The errors between the neighboring times. Right? So in this way, I apologize, that's a mistake. It's not should not be F. This is just a normal norm, vector norm, not the Frobenius norm type of here. So we have a situation where we would like to minimize this expression, find U by minimizing this expression. Let's say we use a L2 norm for vector norm. Then this expression is nothing but actually a quadratic polynomial with respect to matrix elements of U. However, we need to restrict ourselves to the constraint that the U has to be unitary, and that's not a polynomial constraint. So that's actually kind of a nasty constraint to take care of, right? So this is the most kind of basic thing that you can write down. It's easy to write down. It's actually really hard to solve in practice, computation. Now, but there is a trick that we can borrow that actually turns this rather complicated nonlinear polynomial optimization problem into really simple optimization problem. And here's the trick. It's actually, so just zoom window here. The trick is this. We can employ what's known as Kelly transform. It's actually parameterization of a unitary matrix. Any unitary matrix can be written in this form where A is just a Hermitian matrix. This is a very beautiful formula. So it's Kelly transform, known as Kelly transform. So your unitary could be parameterized uniquely by by a Hermitian matrix. Now, if you substitute this expression into here U, and then actually moving and actually then we can move around this inverse operation to the left, basically multiplying this 1 minus IA by the right, then actually this expression can be turned into this minimization objective function. As you can see, that A right now enters, there's no inverse because inverse has been moved, as I said, to the left, right, to this left. And as a result, actually A enters linearly under the sign of the norm. But once you take the norm, you again get a quadratic expression with respect to the matrix element of A. However, A here, as I would like to remind you, is just a Hermitian matrix. And it's actually, the fact that it's Hermitian is just the way you parameterize the matrix elements of A. Therefore, this problem is actually reduces effectively in practice, is nothing but unconstrained minimization of a quadratic polynomial, where the unknowns are the matrix elements of A. Now, so there is something very special about quadratic polynomials. The fact is that they have a global minimum, right? They have a unique and global and unique single global minimum. So, so this problem is remarkably easy to be solved computationally. In fact, it can be just reduced to finding single value, performing single value decomposition. So it's a very efficient way of solving this problem, and it has a unique minimum. Once you found A, you can go back and utilize Kelly transform to recover that underlying unit evolution. So as you can see in this
question.
Yes. Please, actually, anytime questions.
So, you know, measurements always have a noise.
Yeah.
So it's not going to be, how bad that is that for this type of optimization?
So I will show you it performs very well, right? But that's the next slide. That's next slides where we can go to more realistic scenario. Yes, it works really well. But the key of this slide is to show that by having a time sequence of data, which could be just wave function, or it could be actually measurements, actual signals, like for example QI planes from IBM computer, or what other actually raw hardware data, right? Could be also used. You can transform into the problem of polynomial optimization, and in this case, this particular case, right? Is extremely beautiful formulation, which has a unique. So that's like, I mean, it's amazingly. It's just this is what you want to have, right? With all the guarantees of convergence for your optimization. Any other questions? So that's what we would like to. We would like to take this idea and generalize it to more realistic settings, where you have noise, where you have a openness, and you don't have wave functions. So as I said, throughout this talk, we are right now switching to realistic system where you have some quantum device denoted by this box, and you have initial state which is given by a density matrix, and you know the quantum device of performs some kind of unknown operation, quantum operation, which takes delta t time, right? It takes delta t time, and maps the initial state into the first state, zero state into the first state, right? And we assume that we can perform tomographic measurements such that we can actually recover, we can basically, that we are given the sequence of the density matrix. Also, alternatively, right, we can take the same initial state and you can kind of run twice the same operation, and you get row 2, which just means like you have 2 time steps, and so on and so forth. If you have 3 times run the same operation, you have row 3. So we assume that we are given this time series of the density matrix, which characterize the duration of the operation of the quantum device. So, and we would like to take this information and convert it into the model of the system. So that's the data. But in future work, we are planning to extend this formulation where instead of assuming that we have done a series of tomographic measurements, we actually operate directly on the raw outputs of the system. Raw measurements, like direct measurements. So as we know that if you have an open system, right, if this is an open system, then the most general form for which describes transformation of the initial density, input density into the output is given by the Kraus map. The Kraus map formulation, which is given here, where if L is equal to 1, this is just a unitary evolution. If L is more than 1, that's actually describes truly open evolution. So the matrices E's are arbitrary, as you can see, but they have to satisfy this important constraint, which ensures trace preservation of the evolution. So this is a Kraus joint map known, very well known quantum information science. So again, if we have an n time series of these maps, like sorry, not the maps, but the wave functions and the density matrix, right? Then we can actually just take all of them, take left-hand side minus the right-hand side, as shown here, right? And take the norm and sum over all the available time steps. And we can ask a question that we would like to minimize with respect to the unknown matrix E. So we are minimizing with respect to the matrix elements of E. And E here is an absolutely arbitrary matrix. However, it's good to enforce this trace preservation constraint as given here. So it turns out that the best way to enforce this is to formulate this in this form. When you again take a difference of the left-hand side and the right-hand side, and take absolute value norm, Frobenius norm. This is right now Frobenius norm, because this is all these expressions contain only matrices, and the Frobenius norm squared. Now let me remind you that the Frobenius norm square of a matrix is actually sum of absolute value square of each element of this matrix, right? So once again, so Frobenius norm is the sum of absolute value square of each element, which is the argument of this norm. So in this way, the objective function given here is a polynomial function, polynomial expression with respect to the unknown matrix elements of E, because the rows are given, as well as it's also at the same time subject to a constraint which is also polynomial with respect to the same unknowns. Now, but as you can see, unlike the previous example, this example, where the objective function was a quadratic polynomial with respect to unknown, this is the fourth order polynomial, right? Because E comes into multiplication. This is the fourth order polynomial, both the objective function and the constraint. So it's not a longer quadratic. So we actually have to, the question becomes, what about, what kind of properties does this problem have, right? It's not like a quadratic, which you immediately can say, okay, it has a unique solution. So this is actually this is the key formulation. Any question about this slide, or maybe any other previous slides? So it turns out, so obviously the polynomial in general, polynomial optimization problems are very hard. It's hard to actually to say something about. But there has been an amazing progress in understanding the polynomial optimization problems in the last 21 years. Tremendous. There's a major breakthrough done in 2001. So the whole beauty of the main strength of our project is that we try to formulate the problem in terms of polynomial optimization. And there are now very well developed techniques for polynomial optimization, which have guarantees. So if you can reduce your problem to polynomial optimization problem, it's a great news, right? It's no longer the case that this is some nasty disaster, basically, right? Which you have to resort to heuristic. It's actually that right now there are many algorithms available, which are, some of them are summarized here actually. This is the table taken from our preprint. So for more details, follow those references from the preprint. Pardon me?
I have a question. So
yeah,
when you say convergence guarantees, that's only for local optimum?
No,
okay,
no, global. Yeah. It's very important. Global convergent guarantees. And this is a really, because yes, these problems are actually in general nasty, right? Polynomial is general nasty. It has it has many local minima. But there are right now algorithms developed that gives you accurate upper bounds basically on the local minimum. I would like to highlight two libraries which implement this global that find global minima for optimization. By the way, these methods not only work with the minimizing the polynomial cost function, but they also work with the problems that have polynomial constraints, like the one we have here, right, in Kraus, and also polynomial inequalities. So it's a really as generic as it gets. So if you can, so this is the main message of my talk, right, which goes beyond the subject of this of system simplification, is that if you can reduce whatever problem, right, whether it's in agriculture, life sciences, whatever, quantum science, the problem of minimizing polynomial cost function under the polynomial constraints, which could be equalities or inequality, bingo. Like right now, there are cutting edge mathematics tools that can tell you a lot about the global solution to this problem. Now, this I learned hard way, guys. These libraries are not there. You can see this is one of it's for Julia and the one is for Python. Are actually, they're not equivalent. They're different. They're based on different methods. There's actually also one for MATLAB, but since I don't use MATLAB, I didn't list it. Since I didn't use it, so I didn't list it. But it's also very good. It's a MATLAB. You can find the name of this library in any of this Julia or Python version. There are different libraries that they implement different versions of the algorithms for global optimization, and they perform very different. They do different things. They're not equivalent, basically. That's what I'm saying. So these methods, they're relatively new, right? And you can see there's not yet like kind of settled tools for this, like like a LAPAC, right? Like if you want to find eigenvalues, you use some blast LAPAC routines, right? And you get the result. You don't need to bother. But this is not yet the case in this community, right? These things are still under development. As you can see, progress has been made every single year. Now, the idea how these methods all work, general idea of this method is that the global polynomial optimization problem is reduced to a sequence of semi-definite programs, and the sequence is sort of ever growing. Like means each time it's a larger and larger semi. And the larger you go in the sequence, the more precise bounds you get on the global minimum. Right? So this is what it actually stands here, asymptotic convergence. So it means that as you go into along this line into, it's called moments of hierarchy. Higher you go into the hierarchy, the higher the approximation to the global solution you get. Now, in this table, we also list something which is has nothing to do with the global methods, global polynomial optimization, but it's a very important method, BFGS, as it is known in many computer languages, in all the computer languages, basically. It's it's a advanced conjugate gradient implementation, very efficient conjugate gradient implementation that is works on as conjugate works on any objective function, right? Obviously, it gives you a local solution, therefore it has no guarantees. But it turns out, as I will show you in a second, so we actually this is the easiest thing to use, right? Because it's built in all the languages, and turns out that even using this simple conjugate gradient algorithm actually gives you extremely good results, and basically in almost all the cases with noise, which is funny. Actually, noise helps. It leads you to global solution also. So it just happens somehow that to this formulation that we present here and the next one for the Lindblad equation, even heuristics give you practically very good results. So let me show you how we test our methods. So what we do is that we begin by generating generated random master equation, Lindblad master equation. We use actually QTIP for the simulation. And having generated random master equation, like with random Hamiltonian, with random dissipator, with random initial state, we actually solve this initial state to get time series, which we call raw exact, right? It's going to be time series of 50 density matrices for a qubit. We get this time series for exact. Then on top of it, we actually add a noise, which is a random, absolutely randomly generated matrices, density matrices, and we take a convex conjugation with the exact result, such that we get a noisy density matrix, where W measures the noise intensity, right? And we vary the noise intensity. Then we actually use this noisy data set to do system identification using the methods, the formulation that we presented, just presented for Kraus, and the one also for the Lindblad. So we do the same thing. We do the same test for Lindblad. So we take this and put here this density matrices into this formulation, and then perform this minimization. After we get the Kraus map, right, the model, we actually, since you have a model, you can actually recover the time series, right? You can recover the time series, and you will get a time series of density matrices, which we call raw system identified density matrices. Right? So it's from the time series from the identified model. Of course, they are not guaranteed to be exact, right? Exactly the same as this true not noisy, right, data input. And then what we do is actually we perform to characterize the quality of the reconstruction, we perform calculation of the fidelity for each time step, and we find the minimum fidelity, right? So we find the minimum fidelity for the exact time series and the recovered time series for system identification. We compare them. So how well is our model reproducing the data? And we actually perform almost 500,000 tests. We repeat this algorithm 500,000 times to get a good statistics, to get a really good feeling for what's happening. And here's the result of performance. So this is the basically number of tests, the probability, this is, you can say, probability distribution of as a function of this minimum fidelity, as also for a different amount of noise. So as you can see, if there's no noise, we basically get a delta function. We basically get highly peaked, accurate recovery at 1 delta 1. Now, if you start increasing the amount of noise, right, add mixing, convexity mixing random matrices, this tail gets basically, right, the spread of this minimum fidelity, which is against the metric, the worst case scenario, like measurement, the worst case metric of measurement gets larger, but it's actually, even for noise levels of like 10%, the fidelity never drops, right, below 96. And I would like to emphasize, ladies and gentlemen, that this axis is in the logarithmic scale, right? So these tails are in fact really tiny. Most of the reconstructions are actually give you very, very high accuracy, very high accuracy. And I would like to again emphasize that these results have been obtained using heuristic, not even those fancy actually algorithms. Actually, those fancy algorithms are tricky to use, as I said. It's not there are no tricks. And moreover, if you have a non-zero amount of noise, this is very funny. Turns out that the local search heuristic actually almost always, statistically speaking, gives you a global answer, which is really interesting. Which is not the case if you have actually zero noise. Somehow zero noise, there are more false minima actually than actually non-zero noise. So once again, right, so we reduce the problem of quantum channel tomography, right, reconstruction of quantum Kraus maps to polynomial optimization, and showing that even using heuristics, simple heuristics, actually gives you good results with a quite realistic kind of settings. Any questions about the Kraus map reconstruction?
No.
Okay, so and final section is that about recovering Lindblad master equation. So up to now, delta t there was no constraint on delta t. Delta t could have been large, could be small, doesn't matter. Now, if we want to recover a Lindblad master equation using techniques of polynomial optimization, we make an assumption that delta t is small. It needs to be small. So we have to take a small time steps. So this time series of density matrix is kind of a, they're neighboring, like small in time. So this is actually kind of, and again, if you like have in mind real hardware like IBM, actually this is achievable, this is doable. These quantum machines, they have ability to kind of resolve very small time evolutions. So this is not a constraint. Now let me remind you how the Lindblad master equation looks like. The derivative of the density matrix is equal to this quantum Liouvillean, which is given by this expression. The first term describes just unitary evolution. This is the commutative of the Hamiltonian, Hermitian Hamiltonian, and the rest is just the dissipator, where A could be an arbitrary matrix. So what we do is that we can the fact that we assume there's no controls here, no time dependency inside the evolution. We can actually write the mapping between the initial density matrix and the final density matrix via the matrix exponent of this Liouvillean, right? Now, of course, this is, exponent is a really bad function because it's actually not a polynomial function. Actually, in practice, it is a polynomial function because, as we know, right, matrix exponents via Hamilton-Cayley theorem, right, it always can be written as a polynomial, matrix polynomial. But finding this polynomial actually computation is very, very challenging. Actually, it's not trivial. So what we need to do is the following transformation. First, we actually use analog of Cayley transform, which is kind of a total analog of this here, to represent, to express the exponents through these tangents hyperbolic expressions. Now, this is actually a simple identity. This is kind of, high school identity. You can derive this, it's not nothing quantum mechanical about this. It's just a property of exponents. But what's important is that the hyperbolic tangents for small delta t has a nice Taylor's expansion. And if you actually now restrict ourselves to the leading order terms, which is just a linear, what we in fact get is a Padé approximation for the exponent. The good thing about this approximation is that it could be improved, right? We can add more and more terms in systematic fashion by utilizing higher order terms in the tangent hyperbolic. But for here, we actually get the leading term, and this representation is accurate up to the cubic order. And again, I would like to remind you that the Padé right approximation is when you approximate a function by a fraction, and this one turns out to be very productive way of doing for the exponent. Now we can take this Padé approximation and plug it back into this connection between the initial and the final density matrix. And again, dividing by multiplying by the denominator, we obtain this this formula. Right. Now, this is actually, if you ever done, of course, many of you did, right? Quantum evolution. This is nothing but Kranz-Nicolson method, numerical method, implicit method of solving time-dependent evolution, where the unknown, right? Unknown function not only basically enters, so basically you end up on the linear equation onto the unknown function, which is the density matrix in this case, at the next time step. Now taking now the difference between the left-hand side and the right-hand side of this expression and utilizing the fact that the L is linear operator, we obtain this formula. And finally, we just needs to take absolute value square, meaning norm square, Frobenius norm square, and sum up over all the recorded time steps, and we'll get the cost function. And notice here, and so voila, we got our polynomial optimization formulation for the recovery of the Lindblad master equation. And this is unconstrained problem that we just need to take H to be real, Hermitian and arbitrarily matrix A, matrices A. And so, and again, I would like to emphasize that the unknowns enter through this Lewillian, which is given here. And again, this is a kind of a fourth order polynomial optimization, but unconstrained. And the only constraint here is that the time step here should be small. It should be considered to be small for this representation to be accurate. So any question about this formulation?
Sorry, I'm trying to understand how much data one has to take.
Yes, it's a good question. We are still studying this problem. For simulation that I'm telling you, basically we already understand how minimum data we need actually. So for now we have a qubit. All the simulations done on qubit, and we take 50 density matrices to get all these results that I have already showed you, and I'm about to show you next. So it's not much data. It's much less. It's significantly. It's basically it's not a lot of data. 50 density matrices, but we are right now investigating how much we can reduce this also.
Right, so you're not making any structure or sparsity assumptions on the Kraus. So, for example, you're not assuming there are only a few Kraus operators. It could be the entire set.
Yeah, it can be entire set. Exactly. We don't assume that, but right now our tests are restricted to, because it's a qubit, we restrict ourselves to simplest case of two channels.
Okay, so maybe when you're done, we'll circle back to this, because I think that's a important point.
It is important, and I agree.
Yes, so I have a related question, which is like, so what do you baseline this against? Like, what do you benchmark this against? Is it process tomography or something like?
So we are going to actually benchmark with respect to other SID methods. Like this, that's what we're going to add this benchmark in this next version of the paper before submission, please. Yes, but I have to say that this is that would be a. But these formulations that we come up with are actually a result of a very hard labor. Let me put this way: we tested, we played a lot with many formulations. So this is one of them. I will want to show you a next formulation, another formulation, which is very different. The next step, if unless there are more questions.
No, go ahead.
By the way, I wanted to mention why we decided to invent new methods, actually, not just because we wanted to invent new methods. The reason was that it turns out that incorporating constraints like a Kraus constraint, right? The mapping between has to be of Kraus form, or asking that for the master equation to be of Lindblad form. These things are actually super hard for system identification and are quite unnatural. It requires a drastic reformulation of the problem. And we found many preceding works, this constraint was incorporated in a very not in an organic way. And it was not therefore giving us good results. And so this is why we decided to find out something much more hopefully straightforward. And this is really as simple as it gets. So another way of finding polynomial optimization formulation for recovering Lindblad master equation is to simply recall that the master equation is again differential equation. And if I integrate both the left-hand side and right-hand side from some initial time t0 to some intermediate time ti, this integration simply turns the left-hand side into the difference of the matrix at the initial time, 0 time, and the ith time step, right? And that's the right-hand side. Now, so basically, we turn differential equation into integral equation. There's nothing sophisticated about this. We can further simplify this expression by recalling that L is a linear operator, therefore it can be written in this form, right, as L of the integral. And finally, we can take the difference, right, the right-hand side and minus right-hand side, left-hand side minus right-hand side, and take the norm, again, square difference, and we obtain another formulation for recovering Lindblad master equation. So it's a very different integration formulation, which we call an integral formulation. This integral could here be estimated, and by the way, there's no assumption on delta t anymore, right? There's no error bar here. Of course, this integral will need to be estimated. For example, we estimate using trapezoidal and Simpson rule to estimate the value of this integral. Right, so you can be creative, come up different formulations, right? Again, as I said, different formulations for the problem of optimization. And here's results using again the same data sets as I described before. And this is the PADE, right? A method. This is integral method that I just showed by trapezoid, where the integral was estimated using trapezoidal rule, simple trapezoidal rule. And this is the integral formation where integral was estimated by a Simpson rule. And as you can, if you look at this plot, you can see that they're actually kind of performing pretty much the same way, right? Pretty much as if you have zero noise, actually like this delta function, right? No noise delta function, and then as you add more noise, right, you start recovery, quality of recovery drops, but not but in a very accessible, very permissible way. And again, these results have been obtained using heuristics. However, there is a caveat. Here I plot results which converged. Now, it turns out that the methods, the three formulations, even though they're actually kind of looking quite natural, right? The PADE method and integral method formulations from mathematical point of view, from practical point of view, there is a difference actually. So PADE formulation turns out to be always converged. This is per percentile of converged tests, means tests that were able to reach minimum within a given tolerance. Basically, as a level of noise. It turns out that the PADE formulation is very robust. It always converges, always reaches minima, right? It sometimes could give you local minima, right? Especially in the case where there's no noise, but it always gives you noise. It always converges. Whereas the integral formulations, which is trapezoidal Simpsons, they actually converge only in about half cases. This is a very interesting behavior, and I would like to emphasize this is a result. This convergence, failure to converge, is only with respect to the heuristic. Right? Only with respect to the heuristic. We are right now trying to investigate this behavior and trying to see, for example, what these global methods, which method would give us. Right? So as you can see, right, I'm trying to be here honest, telling that these methods are for convergence, they powerful, right? They require some work, but surprisingly, in most of the cases, if you're clever enough, for example, with PADE, you actually can get away with the heuristics. Heuristics behave as good as actually global methods, and heuristics. Let me, guys, tell you, the heuristics are actually cheaper, much more cheaper competition, much more cheaper. Right? Not surprising. There's no free lunch, right, in life. But you have to be careful. Not all the formulations are made equal. Right? as far as heuristics are concerned. So we summarize, right? So we've come up with a polynomial formulations for the problem of quantum systematification, which are very efficient. Kraus actually also always converged. Kraus will always converge, obviously. And for that, these two actually perform very well within heuristic. And so more surprising to our case, and this is why heuristics are permissible, is that it's basically statistically always leads to global optimum if you have noise, and noise is always right the case in the heuristic system. Now we are actually trying to show what happens if we actually switch to global optimization polynomial methods. And what I didn't put here is that these methods are kind of easy to extend if you have a driven systems, right? So we have not assumed anything about the system. There is a driving instance. We assume that the generator of motion, Hamiltonians, had no controls, but this can be easily, very naturally extend to case of present control. We are working on this. And also the same formulations with little kind of, with a little change of the kind of emphasis of the problem, we have actually new algorithms for quantum control problem. Right? The same ideas could be used with the problem of finding control pulses to get you to do what you want. So yeah, thank you for your attention. That's everything that I wanted to say. And yeah, please ask more questions.
Thank you so much. So we already had a few questions. Do we have any more now? Shai, anything else that you wanted to catch up?
Yeah, so am I muted? No, I'm great.
No, you're good.
Okay. So two things really. One is the recent interesting work from Ian Seizert on shadow tomography.
Shadow tomography. Mm-hmm.
And there they make quite strong assumptions on the structure of the Hamiltonian. And by making such assumptions, they significantly reduce the amount of data that needs to be taken. I think that this might be valid here as well, meaning if I assume there are only two leading Lindblad terms, for example, okay, and not the n squared possible Lindblad terms, or I don't remember, it's n squared, whatever it is. Well, if it's diagonalized,
one, but yeah.
Yeah, if it's diagonalized, then it's n. If it's not, then it's squared. Then maybe you can kind of make do with a lot less data. So from my perspective, the most expensive resource here is the data that you need to take. So I would compare this to other methods of getting the same information and what would require more data. That's one thing. And I don't have a good feeling. For example, if let's say I want to let's say I want to do just a gate tomography. How does this compare in terms of the amount of data taking necessary? And then kind of take it forward to Lindblad or a channel. I don't know the answer, but I'm very curious.
So we are working on understanding these limits. It's a very, very important feedback. When we started this project, actually, we were not too much concerned about this, but because we wanted to make it work.
Yeah,
we were considering making it work, but now we are investigating, and apparently, what's interesting is that our collaborators from Prague actually have been recently able to put some theoretical bounds, rigorous bounds on the amount of the data. And so some basically sampling like that. And the idea is that it's also what's important to realize is also the noise. So it turns out the more the noise you have, the actual less data you need. because having a lot of data actually does not really help. Like, you just get like more, you add redundancy, but that redundancy does not like enable you to suppress the noise. So it's important. Yeah. So there are many factors that go into the game. Not only sparsity of the model, but also the amount of the noise. And we see this as already several times mentioned, that even noise kind of helps you also to perform the minimization. Like somehow when you have noise, we don't see evidence for local minimum, numerical evidence for heuristics, which is kind of amazing actually. Yeah, so we are investigating this stuff. I cannot say more right now.
Okay. But that actually also sounds good, because that means we'll probably have another call like this a few months from now when we have another paper from you or more results from you. Because clearly
actually
this is, yeah, sorry, go ahead.
Maybe one more question. Or hope or request or something. When the paper is published, if you have some kind of Qiskit circuits and code, related analysis code that we can just take and run, that would be fantastic.
Yeah, that's a great suggestion, right? That's sort of ultimately right how it should be. Yeah, and it's easy. It's actually easy to have it.
Yeah. I'm assuming you kind of have to have it anyway.
Yeah.
But yeah.
Yes, that would be in fact, our actually collaborators from Czech. Actually, that's how it started. Actually, because Jakub actually before joining becoming the faculty, computer science department, he actually worked at IBM. So this is, yeah, you're asking the right question.
Okay, great.
So
the group at Army Research Lab, they are an experimental group, or they are also?
No, this is the theory. This is theory actually. This is theory. In fact, so the Kurt Jacobs, he actually was interested in deriving, studying actually kind of, as many of us have fed up with the derivation of Lindblad equations from the textbook, where you make lots of assumptions and get something, and how well it works, I'm not quite sure. He decided, okay, I have a supercomputer at Army. I can run really, really accurate, exact, giant simulations of a qubit couple to real many boson background, like gigantic simulation, right? You get a full wave function. Now, can I do something with this data to recover actually much more accurate master equation that people use, and without sidestepping derivations actually? And the answer was actually turns out yes. This is the paper that he published, and I was lucky part of this team. And yes, and then after doing the simulations, he actually, using the system indication tools, he was able not only to get new master equation, but also actually was able to get justify derivation, actually come up with a derivation, see which assumption he didn't have to make, that we do make in the textbook version. But there is still quite a larger question persists, that like, okay, so but really, like, what if you don't have, what if you cannot make this, derivations at all, right? So this derivation was made post facto, truly post facto, right? Having actually first got it by this engineering means. And there so data was not a concern for us at the beginning of the project, but that's why I'm bringing this up. There is plenty of way of getting data, including high, really good quality simulations, ab initio simulations of a small open system acting with a real bath, like a real bath proposals, right? Because of the progress in matrix product states, right now the simulations are on, large enough computers are achievable.
All right, so I don't see any other questions. So we thank our speaker once again for this very, very exciting talk. And thank you so much for joining us all the way across from the US. And it was very nice listening to you. And yeah, I'll see the rest of you next week, and goodbye for now.
Thank you, goodbye, have a nice weekend.
Bye-bye.
Bye.